Okay, so good morning everyone. So last class we looked at the basics of circuit complexity. We saw the definition of what is a circuit, what we mean by the size of a circuit, and we saw some trivial upper bounds on the size of a circuit computing any arbitrary Boolean function. Okay. In particular, we saw this n into 2 to the power n upper bound, that any circuit will have computing a arbitrary Boolean function. So, what we are going to do today is we are going to look at some lower bound results, okay, on the size of a circuit as well as the size of a formula computing a Boolean function. Okay. In other words, what we will show is that if we take any arbitrary Boolean function, what is the smallest, I mean what is the least size of a circuit that can compute that Boolean function. Okay. If not for all, maybe for a large fraction of Boolean function, we will show that the size of the circuit is at least some value, or the size of a formula has at least some value. Okay. So, let me start by giving a definition. Okay. The C omega size of a Boolean function is the smallest sized circuit over omega that computes the function. Okay. Similarly, we can talk about the smallest sized formula as well. So, the L omega size of a Boolean function is the smallest sized formula again over omega that computes the function. Okay. So, yeah. So, now let us look at a theorem. So, the first theorem that we are going to study today was given by Shannon. So, this is also called Shannon. Shannon has many theorems. This is one of his very famous theorems in circuit complexity. So, what he showed is that most circuits or most functions over n variable. So, most n array functions, okay, have C beta 2 that is greater than size at least 2 to the power n over n for sufficiently large n. Okay. Okay. So, what do I mean by this? So, what we mean is that so we will show that a very large fraction of Boolean functions over n variables require circuits of size at least this much. Okay. So, for very large class of Boolean function, there are no circuits which have size smaller than this quantity. Okay. And as you can see, this is a exponential quantity. Okay. For sufficiently large n. Okay. So, maybe for small values of n, things can be small, but as n tends to infinity, this bound is achieved, this lower bound is achieved. So, how do we prove this argument? So, before I get into the proof, let me just give some overview or some idea how we will proceed. So, what we will try to do in these kind of results, okay, is we will try to compute how many circuits. So, suppose if I fix n, okay, as the size of the input which is there, and I fix a size s. So, let us say I want to count how many circuits are there of size s over an input of size n. So, I will try to estimate a count for this. Of course, we do not require an exact count, we will just get an upper bound on this count, and then we will compare it with the total number of Boolean functions over n variables. How many functions are there over n variables? How many Boolean functions are there? Yeah, we saw this last time, it is 2 to the power 2 to the power n. Okay. We will compare these two quantities and that will give us this result. Okay. So, that is the standard procedure we will follow. First, we will look at this result for circuits and then we will look at the result over for formula as well. Okay. So, let f s of n be the number of Boolean circuits over B2, number of, let me just say it over here, n array Boolean circuits over B2 of size s. So, we will try to get an estimate on this quantity Fsn. Okay. So, how do we get an estimate on this quantity? So, first of all, look at a circuit. Okay. So, this circuit will have s gates. Okay. Now, each of these gates is an element from B2. How many elements does B2 has? No, B2 is basically all gates with 2 inputs. So, it is 2 to the power 2 to the power 2, which is 16 gates. Okay. It can be anything, it can be any of those 16 gates. Okay. So, the De Morgan basis has 3 gates, and or and not. Okay. So, this is the B2 basis we saw last time. So, okay. So, each of these gates can be one element from B2. Okay. Now, it is a circuit, which means it is a directed acyclic graph. So, each gate, so totally how many nodes are there in the directed acyclic graph? How much? How many gates are there? S gates. How many input gates are there? N. So, what is the total number of nodes in this circuit? So, it is n plus s, right. So, all the input gates or all the input variables plus all the non-input gates. Okay. So, it is n plus s. Now, fix a gate. Okay. Let us take any particular gate. So, from how many gates can it take input from? Okay. So, it can take its each gate has 2 input wires coming to it, and each of those input wires can come from any of the other n plus s minus 1 many nodes in this circuit, right. So, the total choices or the total number of choices for inputs to a fixed gate is n plus s minus 1. Anything else? I am not talking about the input gates, I am talking about the other gates. Okay, these S many gates. So, I have S many gates. So, each of those S gates can take its input from any of these n plus s minus 1 many gates. Okay. And there are two inputs to a particular gate. So, this will be n plus s minus 1 whole square. Yes, this can be anything from B2. I am only looking at the input to these gates right now. Okay. Now, this can be any element of B2. B2 has 16 element. Okay. So, which means that the yes square means that. So, suppose if I have a gate, okay, let us look at a gate. Okay, let us look at a pictorial view of this. Okay. So, I have some gate, okay, let us call this as G. Okay. First of all, G is an element of B2 and G takes input from two other gates, G1 and some G2. So, for G1 there are this many choices, for G2 there are this many choices. So, therefore, the total number of choices for G is this square. Okay. Now, how many choices are there for this G itself? 16 many choices, because B2 has 16 elements. So, therefore, for the gate G, we have 16 n plus s minus 1 whole square possibilities. Okay. So, this is for a single gate. No, so G can be any of the 16 gates. Okay, so this G can be any of the 16 gates that are present in B2. So, there are 16 choices for G, there are n plus 1 minus 1 choices for G1 and there are n plus s minus 1 choices for G2. Yes. Okay. Now, so this is for a one particular gate, right. Now, the point is that I have a total of s many gates. Okay. So, the okay. So, before I write that total, okay. So, therefore, the number of possibilities for a circuit of size s over n variables is, so each of the gates. So, now I have s many gates, each of the gate can be one of these possibilities. So, it will be 16 n plus s minus 1 whole square whole to the power s. Okay. Now, here actually we are doing a very gross over counting, because we are also counting, we are also looking at. So, let us say if I have, suppose if I have let us say 3 gates G1, G2, G3. Okay. So, G1, G2, looking at a circuit which has this G1, G2, G3 and G2, G3, G1 are basically the same. So, basically I am not considering, so basically I am looking at ordered tuples of gates over here. which is not required. Okay. So, what I need to look at is unordered tuple. So, I will divide it by s factorial. Okay. So, this is because the ordering of the gates does not matter. Okay. So, whatever order I write the gates in, it is basically I am looking at the same circuit. So, this is the total number of possibilities for FSN. Okay. So, my F S of n is upper bound. So, again as I said that this is just an estimate, this is an upper bound is 16 n plus s minus 1 whole square whole to the power s divided by s factorial, right. Again, so basically the way I am counting circuit is I am looking it as a DAG and I am trying to count all DAGs which has a certain structure and how many such DAGs are there, right. Now, it can very well be possible that some of those DAGs even do not represent a circuit, that can be possible. I do not care about it because I just need a upper bound in this case. Okay. So, now let us try to simplify this quantity over here. So, first I will use Stirling's approximation for s factorial. So, I can write it as 16 to the power s plus n minus 1 whole to the power 2s divided by s to the power s divided by. So, Stirling's approximation is s factorial is greater than or equal to s to the power s divided by 2 to the power s or e to the power s, I think. Yeah, e to the power s. E to the power s. So, this I can write as 16 e whole to the power s. So, I will take this s outside. So, this becomes s to the power 2s 1 plus n minus 1 over s by 2s divided by s to the power s. So, this 2s and s cancels out. So, we get s to the power s over here. So, what we have here is okay. So, before let me just say something. So, this quantity, so can you give a bound upper bound on this quantity 1 plus n minus 1 over s? Huh? So, what can we say about n minus 1 over s? Huh? I am sorry? Which one? S is bigger than n. Let us, yeah. So, n minus 1 over s is at least less than 1, that is all. Okay. So, this quantity is upper bounded by 2. Okay. So, I will just keep that as the bound. So, what I get is, so 2 to the power 2s is 4 to the power s. So, this becomes 64 e to the power s. So, I mean we cannot say it is half or anything. I mean n can be, let us say n can be n minus 1 by s can also be like 0.9. We can't say it is half. So, okay. So, it can be anything, but we know that it is at least or it is at most 1, it cannot be more than 1. Okay. And now, this is s to the power s. Okay. So, this is a constant 64 e. So, this is actually this is equal over here. Oh no, this is less than or equal to. So, this is equal to c to the power s times s to the power s for some constant c. Okay. Now, we have this quantity over here. So, we will now take a value for s. Okay. Now, so let us say we set s to be 2 to the power n. So, what is the bound that we wanted? We wanted 2 to the power n by n. So, let us set S to be 2 to the power n over n. So, S was an arbitrary variable for us, we can set it to any quantity that we like. So, we will set S as this, and now let us see what this quantity becomes. So, f s of n is c to the power 2 to the power n over n times 2 to the power n by n whole to the power 2 to the power n by n. Okay. So, this would, how can we write this? So, this becomes equal to c by n. So, I take this n outside. So, c by n 2 to the power n by n, and this is times 2 to the power n times 2 to the power n by n. So, this n and n cancels out. So, we get c by n 2 to the power n by n times 2 to the power n. Okay. So, what can we now say about this quantity on the left hand side? Any guesses? C is a constant, n is a arbitrary quantity. In fact, we assume n to be sufficiently large. So, what can we say about this? It is a small number, in particular this quantity is less than 1. We can assume that for sufficiently large n, this is less than 1, and if this is less than 1, what can we say about this? This tends to 0. So, as n tends to infinity, this quantity tends to 0, and what is this? This is the total number of Boolean functions over n variable. So, we can write this as small o of 2 to the power n. So, what is small o notation? So, again for those of you who are not familiar, small o means that this quantity is asymptotically smaller than 2 to the power n. Okay. So, therefore, actually the proof is over now. Therefore, for most Boolean functions, we require circuit of size greater than or equal to 2 to the power n over n, because this was the number of circuits which is much smaller than, asymptotically smaller than the total number of Boolean functions. So, therefore, for all remaining Boolean functions, we require circuits of size greater than s. So, any questions? We say a circuit. Yes. Yes. Overall. N-ary means that the circuit has n inputs. The circuit is over B2, which means that each gate is an element of B2, which means that each gate has a fan in, or each gate takes 2 inputs. Okay. So, I do not think I formally used the word fan in last class. So, fan in of a gate means the number of inputs to that gate. Fan out of a gate means the number of outputs from that gate. So, the moment we say that the circuit is over B2, it means that the fan in of every gate is at most 2. Okay. Any other questions? Yes. Think of the DAG, the directed acyclic graph. So, what we said last class is that a circuit is a DAG. So, think of that DAG. How many nodes are there in that DAG? Okay. That is what we are referring to over here when we say n plus s. Here. Okay. anything, yeah.
So, the quantity 2 to the n by n, we can put any constant in the denominator. 2 to the n by cn.
You can put, yeah.
Then but we cannot put n square, no? 2 to the n by n square.
No, no. So, I want to put a quantity which will simplify to something that I can work with. You can put anything for S, okay, but I want to put a quantity that would simplify and give me a asymptotic quantity like this.
Factor of 2 to the n there.
Yeah. You can put anything for S, nobody cares, but I want to put something which would simplify and give me a quantity like this, where it is 2 to the power 2 to the power n multiplied with some quantity that tends to 0. So, now as I said that we would look into, so this result was about circuits. Okay. So, we showed lower bound on the size of most circuits computing a Boolean function. Now, we will try to give a similar lower bound for Boolean formula as well. So, lower bound on the size of a formula computing a Boolean function. Okay. So, what is the difference between a circuit and a formula? So, formula is a tree. Yeah, so for a circuit, the out degree of a gate, the fan out can be more than 1. For a formula, it is at most 1. Okay. In other words, the DAG is a tree over here. Okay. Okay. So, theorem. So, this theorem is by Riordan and Shannon. So, let delta be a quantity smaller than 1. Most Boolean formulae require, or sorry, most Boolean functions require okay, let me just rewrite this. For most Boolean function f L B2 of f is at least as large as delta 2 to the power n by log n. Okay. And here what we will do is, I will just make a small modification to this theorem. We will not look at the total number of gates, we will look at the star size of the formula. Okay. So, remember what we meant by star size. So, star size is basically counting the number of OR and AND gates. Okay. We will not count the number of NOT gates, and we will actually consider this yeah, we will not count the number of NOT gates. Okay. So, I will refer to this as L star. For most Boolean functions f, the star size L star B to f is at least this quantity. Okay. So, let us just try to understand the difference between this theorem and the previous theorem. On the previous theorem, so which of these two quantities is larger? So, previous theorem we had 2 to the power n by n, here we have 2 to the power n by log n. Okay. So, this is a larger quantity. So, essentially this is a more, so this is a better lower bound. Okay. So, what we are saying is that the formula would have an even larger quantity, which is what we expect, okay, because the formula is a more restricted version of computation, it is a more restricted computational model. Therefore, we expect that the size of the formula to be larger, which is what we get from this theory. Okay. So, how do we get this denominator of log n instead of n? No, I use this thing L, na. So, I gave the definition earlier. So, look at the definition that I gave, that C omega is the smallest size circuit computing a formula, and L omega is basically the smallest size formula. Okay. Yeah, I can write it as well, the star size of a formula for the function comma L star B2 of f. Okay, actually I have a name for the function, so let me use the name for the formula computing f is this much. Okay. Okay. So, now the question is, how do we count the number of Boolean formula? Okay. So, before we get into how we count the number of Boolean formula, let me just talk about a notation for representing Boolean formula. Okay. So, how can we so what is a Boolean formula? Pictorially a Boolean formula is a tree. Okay. How can we represent, and we are looking at binary trees over here. So, it is a binary tree. How can we represent a binary tree? So, binary tree can be represented in many ways. So, there is in order notation, there is postfix notation, there is prefix notation. So, we will look at the postfix notation, and I will tell you very soon why we consider postfix notation. So, what is postfix notation? Let me quickly talk about it. The postfix notation for a Boolean formula has the operands before the operator. Okay, so this is actually a very crude definition, a very informal definition, but this would be enough for us, because let us look at it with some examples, okay, couple of examples. So, suppose I have a Boolean formula x or y and then and z. Okay. So, what would be the postfix notation for this Boolean formula? So, any guesses? So, it would be, I want to compute this first. Okay. So, it would be x, y or, and then to the result of this I am conjugating z. So, it will be z and. Okay. Now, for the same order, if I have x or y and z, where y and z is computed first, what would be the postfix notation? Huh? No, it would be again x, y, z and or. Okay. So, I would keep on looking at the operands until I get an operator. So, the moment I get an operator, I look at the previous two operand, which is y z. So, I do y z and I get that result, and then with that result I do or with x. Okay. So, the point is that if you look at the relative order of the variables, they remain the same, which is the same case as over here, but What is the advantage of postfix notation? Huh? It eliminates the requirement of brackets or parentheses. You do not need. So, once you give a postfix notation, you do not need to put parentheses anymore if you write the notation carefully. Okay. So, this is why we use postfix notation. So, postfix notation eliminates the need for parenthesis. Okay. So, this is the infix notation or the standard notation that we use. Here, if we do not specify the parenthesis, it could mean either of the two precedences. Okay. So, either this can get precedence or this can get precedence, unless you have a specified order of precedences, but here you do not need to specify that. Okay. And this therefore, parsing is unambiguous. Okay. Okay. So, why are we looking at postfix notation? The reason why we are looking at postfix notation is because what we will count is that for a Boolean formula of a fixed size, how many different postfix notations are there. So, consider a Boolean formula of size S. Okay. Now, how many ways can I write this string? So, first of all, how many characters will be present in this string? And assume here that there are no NOT gates. Okay. So, each gate has a fan in 2, let us assume that. The reason why we assume this is because we are only computing the star size, okay. That is why. How many or before I even get into the number of characters in this string, think of a tree which has S internal nodes and some n leaf nodes. What would be the size of this tree? So, that tree size will be n plus s minus 1, right. So, now consider this formula. Okay. What would be the number of characters in this formula? So, actually it is not n plus s minus 1 over here. Why is it not n plus s minus 1? Yes. So, the same variable can be repeated. Okay. So, when you say n plus s minus 1, you are assuming that for every input variable you have a single gate, but that need not be the case, because it is a tree. The same variable can go to different, I mean if the same variable has to go to different gates, you need different copies of that variable. Okay. So, the total number of gates would be yes, how many? S number of gates, but what is the total number of nodes in that tree? 2s plus 1, exactly. Okay. So, any binary tree with s internal nodes has a total of 2s plus 1 many nodes, correct. Okay. So, therefore, the length of the string representing the formula is 2s plus 1. Okay. Now, let us look at a string which has length 2s plus 1 and let us count the total number of possibilities for that string. So, first of all, these gates can be, how many gates are there? S many gates, okay, and these S gates can be in any of the S positions. Okay. So, there are total 2s plus 1 many positions. So, it can be in any of these S positions. So, I have a total possibility of 2s plus 1, choose S many possibilities. So, this is fixing the gate positions. Now, each of those gates can have how many different possibilities? 16 different possibilities. Okay. I mean, not as, it does not matter, it is some constant. So, let us say 16. So, there are this many possibilities for the gate. Each gate can have 16 possibilities. So, it is 16 times S, and each variable can have how many possibility? N possibilities. And how many such variable nodes are there? S plus 1 many variable nodes. So, each of those S plus 1 variable nodes can have n possibilities. So, n to the power S plus 1. Okay. So, this is the number of possible sequences representing a Boolean formula of size S over n variables. Okay. So, we are doing nothing very fancy over here, just counting the number of such sequences. Once again, many of these sequences even need not correspond to a formula. I mean, you can have sequences, I mean, for example, if I have something like a sequence which begins with, let us say, or x y, that does not even mean anything in the postfix notation. We ignore such things. I mean, it is okay, we are just interested in a upper bound. So, now let us try to once again estimate this quantity. So, this again we can use Stirling's approximation over here. So, this is like 2s plus 1 whole factorial divided by s factorial times s plus 1 factorial. So, we use Stirling's approximation over here and we can simplify this to, so this quantity 2s plus 1 choose s is upper bounded by 4 to the power s by Stirling's approximation. Okay. So, now what we have is 2s plus 1 choose s times 16 to the power s n to the power s plus 1 is at most 4 into 16 is 64. So, this would be 64 to the power s times n to the power s plus 1, and I can write this as some constant c times c to the power s times n to the power s plus 1. Okay. Now, we will try to see what this quantity becomes. Okay. So, we set S to be Yeah, so we will set S to be delta 2 to the power n by log n, delta 2 to the power n by log n. Now, let us try to see what that becomes. So, therefore, C to the power S times n to the power S plus 1 is equal to C to the power delta 2 to the power n by log n times n to the power delta 2 to the power n by log n times n. Okay, so, that extra n is coming because of this plus 1 over here. Now, we will do a change of basis and we will write this as a power of 2 over here. So, I can write this as 2 to the power delta log C whole to the power n by log n, and this will become 2 to the power delta log n to the power n by log n. Okay, so let me just check whether this is the correct thing. Okay, so okay, so maybe I might be making a mistake here. So, let us try to do this a little more carefully. Sorry, so this was n to the power this times n, right. So, we can write this as C raised to the power 2 raised to the power n whole delta by log n. Okay. Yeah, and this I can write as n raised to the power 2 raised to the power n delta by log n. Now, I want to write both these as base 2. So, what would that be? So, this would be 2 to the power huh? 2 to the power? Yeah. So, 2 to the power n times log C. Let's just verify this. So, if I take log yeah, exactly. And I do the same thing over here as well. So, this would be 2 to the power into log n delta by log n times n. Okay. So, this log n and log n cancels out. So, what we have is 2 to the power 2 to the power n whole to the power delta, and here we have two to the power n log C by log n times delta 2 to the power 2 to the power n times delta times n over here. So, this is what? One plus log C by log n whole to the power of delta times n, right. So, once again log C by log n is asymptotic, I mean as n tends to infinity, this quantity tends to 0. So, this is very close to 1. So, therefore, this entire quantity is asymptotically smaller than 2 to the power 2 to the power n. Huh? Delta, we can take delta to be any constant less than 1. Okay. So, since delta is less than 1, as I mean no, if delta is 1, this will yeah, then it won't approach, I mean it won't be asymptotically smaller than 2 to the power 2 to the power n. Na? So, if you take delta to be 1, then you have 2 to the power 2 to the power n times 1 plus log C by log n, which can be bigger than 2 to the power 2 to the power n, right, because this quantity is still, I mean this quantity is still greater than 1. So, this quantity is greater than 0, right. So, only when I take delta to be a constant less than 1, this drops down. Therefore, for most Boolean functions, we require formula of size more than 2 to the power n by log n. Okay. Well, for any delta that is less than 1. So, now the next thing that I want to discuss is a very general result. So, I will not be proving the result today, but I will lay the foundations for that result, and then in our next lecture we will look at a proof of that result, and then we will see applications of that result to show how we can show other lower bounds on circuits which have other, or circuits of formula which have other kind of structures. Okay. So, we have defined, let us look at a couple of definition. So, we defined what we mean by the star size, right. So, this we have already seen. Now, let us look at the definition of leaf size. Okay. So, leaf size is simple. So, the leaf size of any Boolean formula is the number of leaf nodes that are present in that Boolean formula. We actually already use that over here informally, but formally we can give a definition. So, the leaf size of a Boolean formula is the number of leaf nodes in the leaf node occurrences in the Boolean formula. Okay. So, again as I said, in the Boolean formula you can have the same variable which occurs multiple times. So, for each different occurrence of that variable we will count it again. Okay. So, it is the total number of leaf nodes, I am not saying it is the total number of variables, it is the yeah. So, this is called the leaf size, and then we have the star depth. So, the star depth of a it can be for formula as well as circuit. So, let me define it in terms of circuit. Of a circuit is the maximum number of OR and gates in a path from an input gate to the output gate in that circuit. Okay. So, it is the you take any path from an input to the output gate and count the number of OR and AND gates present. The maximum over all such quantities is the star depth. Okay. And it well let me also mention what depth is. So, depth is when you just count the number of gates present in that circuit. Okay. It can be OR and not, but when I say star I just mean number of OR and AND. And one more quantity that we would require is what is called the alternation depth of the circuit. Yeah. The alternation depth of a circuit is the maximum number of times a path alternates between and OR gates in that circuit. Okay. So, now take any path, I can have along that path, let us say I can have the gates as OR and OR. So, the number of gates present is 5, but the number of alternations is only 2, okay, because you go from OR to and then from AND to OR. Okay. So, that is what we mean by alternation depth. Okay. So, one quick result about the leaf size, something that we already saw. In any circuit or not circuit, any formula, okay, for a Boolean formula phi, leaf size of phi is equal to star size of phi plus 1. So, all we are saying is that you take a Boolean formula. Okay. Now, when I say leaf size, it means the total number of leaf nodes in that formula, and star size is the number of internal nodes in that formula, and we are looking at we are not counting the NOT gates over here. Now, even if this Boolean formula contains AND or and NOT gates, if you look at a NOT gate, what is the fan in and fan out of a NOT gate? Both are 1, right. So, if you look at a Boolean formula, okay, then the number of internal nodes which have degree 2 is 1 less than the number of leaf nodes. Okay. So, this actually directly follows from the theory of binary trees. So, what else do I need? Yeah. So, one more quantity is related to Hamming distance. So, let take two strings. So, let sigma and tau be two strings of length n, okay, such that sigma is not equal to tau and the Hamming distance of sigma and tau is equal to 1. Okay. So, two strings which differ at exactly one position. Okay. Now, for two sets over 0 1 star, so then we call them something, right? Okay. Then we call sigma and tau as neighbors. If for two strings the Hamming distance is equal to 1, we call them as neighbors. Now, let us take two sets. Okay. So, let A and B be two subsets of 0 1 to the power n. Okay. We define NAB to be the size of the set of tuples sigma tau such that sigma and tau are neighbors. So, what are we counting over here? So, take two sets A and B, and in A and B I am counting that if I take so A and B are neighbors, and so A, yeah, so sigma is in A and tau is in B. Okay, sigma and tau are neighbors, and sigma is in A and tau is in, huh? Exactly. So, if I look at sigma comma tau as belonging to A cross B, then what you are saying is correct. Yeah. So, if I take two sets A and B, okay, how many tuples are there such that one element is in A and the other element is in B, such that they are neighbors. So, that is NAB. So, now we are in a position to state the theorem. So, this theorem was by Kravchenko. So, it is called Kravchenko's theorem. I am sorry.
They can be any sets. they need not
A
be
can A
disjoint.
and B can be anything, they need not be disjoint, they can have common elements. Yeah. Here, in this definition, they can be anything. But when we prove Kravchenko's theorem, we will consider A and B to be disjoint. So, let f from 0 1 to the power n to 0 1 be a Boolean function, and let A be some subset of f inverse 0 and B be some subset of f inverse 1, then what Kravchenko proved is that L star over and or and not of f is greater than or equal to n a b square divided by cardinality of A times cardinality of P minus 1. So, let us try to understand this. So, what this is saying is that if I look at a Boolean formula, okay, and if I look at, let us say, two sets A and B such that A gets entirely mapped to 0 and B gets entirely mapped to 1, A and B can be anything, it is basically a subset of these two quantities. Then the number of pairs, so basically if there are lot of pairs from between A and B which are neighbors, then the complexity of f goes higher. Okay. And if A and B are in some sense very separate, okay, there are not many neighbors between them, then the complexity of f becomes smaller. Okay. So, this is like a very nice connection, okay. It kind of relates the circuit complexity, or in this case the formula complexity of a function with how many tuples are there which are close or not so close. Okay. It is the so f inverse 0. So, f maps strings to 0 and 1, right. So, f inverse 0 is all those strings which get mapped to 0. F inverse 1 is all strings which get mapped to 1. Because yes, it is not equal, it is subset. It can be any subset. Yes, for all subsets this is true. So that is why it is a much stronger result. It is not just for f inverse 0, f inverse 1, but any subset. Okay. And we have this minus 1 because ultimately what we will prove is that we will prove that for the leaf size. So, basically we will prove that the leaf size of a tree is greater than this. So, if I take a binary tree, okay, then the number of leaf nodes is greater than this quantity, which means that the number of internal nodes is greater than this quantity minus 1. So, that is the reason we have this minus 1. Okay. So, we will see this on Friday. So, f inverse is all strings which map to 0, f inverse 0. Okay. So, it is a standard, I mean you should look at the definition of functions. So, this is like a standard notation for functions.
And here in this case A and B will be disjoint.
Of course, because two strings cannot, I mean a single string cannot go to both 0 and 1, by definition they are disjoint. Okay. Okay.
Sir, if there are many neighbors, then this value of L star will get higher.
So, then the bound on L star is higher.
By many, you mean ki the minimum of the cardinality of A and B?
No, By many I mean just if this quantity is large, then this is also large, that is all that I mean.
Can we set a bound on n a b? Minimum of a and b less than the minimum of a and b.
I mean you can set a bound, I mean I do not understand you. So, NAB is basically the number of pairs,
Yeah, number of elements of a or b.
yeah, number of elements from A cross B which are neighbors, right.
Yes, can be maximum. It can take a maximum value of
It can take a maximum value of A times B,
a times b.
yeah.
The minimum of a or b. A to b you are mapping now. So either you can map all the elements of a to some element of a.
See, if all the, I mean it can be, so I am saying that the upper bound on this will be I take all elements of A times all elements of B, let us say all of them are neighbors, that is all, that is what I am saying. That is a trivial upper bound.
Element can have two neighbors also.
It can have more than one neighbor, yeah, and many neighbors. Okay. Okay, so thank you.